Hello and welcome. My name is Alejandro Torres-Orjuela and I'm a PhD student at the Peking University. Today I'm going to present a phase shift of gravitational wave induced by aberration, which is a paper I published a couple of months ago together with my supervisor, Xian, who is professor here at the Peking University, and Amaro-Seoane, who is currently in Spain. The content of my presentation is as following. First, I will talk about moving sources because the aberrational phase shift is related to moving sources. So we want to talk about why we think moving sources are interesting and which kind of moving sources we're interested in. Then in the second part, I will talk about the effect of the motion on the phase. The phase is the most important observer of gravitational waves, and we know they are going to be affected by the Doppler phase shift when there is motion, and also discover this new effect, the aberrational phase shift. Then in the third part, I will talk about the detectability of the phase shift. Basically, how big is the magnitude of this phase shift and how is this going to translate in a signal to noise ratio. Let's start with the moving sources. Why do we think moving sources are interesting at all? This is because most of the moving sources will be moving relative to us. I mean the center of mass of the moving sources, not only the revolving black holes or neutron stars. This is because they are going to be usually in galaxies which have a peculiar velocity relative to our galaxy. They're going to be in systems, so they will be orbiting a central potential in a way. And when gravitational wave sources merge, they suffer recoil velocity. So there are several velocities which will cause the center of mass of a gravitational wave source to move. However, despite this fact, there is no template which can describe the general motion of a source. Like no template can describe all these kind of velocities. Some can describe some of them, but none of them can describe all. So we know that this motion is going to affect the amplitude and the phase. And this is going to be very interesting because this can provide us information about the source itself, for example, due to the recoil velocity, or from the environment, for example, due to the orbital motion. So what we need is a clear understanding of this effect or these effects to be able to describe this motion. But first, let's look at on which sources or moving sources we think are the most interesting ones. First, we think about the kick sources. When you have a binary black hole or neutron star which is merging, and they are not completely symmetric, then they emit gravitation wave in an anisotropic way. And the closer they get to the merger, the stronger is this emission. So the center of mass of the binary starts wiggling around, and while they merge, and right after the merger, they get a strong kick in a certain direction. This kick can go from hundreds to 1,000 kilometers per second, independent of the mass of the system. This makes them very interesting because these velocities are so high that they could even escape the most massive galaxies we know. So for example, for stellar mass black hole mergers, this could have a major impact in the evolution of second, third generation mergers. And for example, for supermassive black holes, this could even have an effect on the evolution of the galaxy itself, because imagine you have two galaxies, they merge, they're supermassive black holes, then merge, and they get kicked out. This, of course, would have a major impact on the evolution of the galaxy itself. The other kind of moving sources we think are interesting are something we call triples, where we are not as strict with the term triples as others. But triples will basically mean just a binary, which is bound and emitting gravitational wave, and somehow circling a third potential. This, as I mentioned previously, is going to happen for almost all sources because they are going to be most likely in some system and can go again from hundreds to 1,000 kilometers per second. Then there is also this very special case of a binary circling around a supermassive black hole, which we think is an extremely interesting case because on the one hand, the velocities of the binary can go up to relativistic velocities, and also because we'll have like one source emitting two kinds of gravitational waves. One, the small binary emitting gravitational waves in probably something like the LIGO band, and the binary which is orbiting the supermassive black hole, something we call binaries in very low frequency band, probably in something like LISA. So we would have one source emitting gravitational waves in two completely different windows, which would allow you extraordinary test of alternative theories of gravity. However, to be able to detect all this and to understand it, we first need to have an understanding of what happens with the gravitational wave. And the most important part is there, the phase. So let's first talk about the Doppler shift, which have been studied previously and for which several people have shown that this is going to be detectable for kicks as well as for triples. The Doppler shift is more or less the following. When you have a velocity along the line of sight, then your frequency is going to change. It is going to go to lower frequencies when it is moving away from you and to higher frequencies when it's moving towards you. Now, what happens with the gravitational wave is, without the Doppler shift, more or less the gravitation would follow the black line. But now, due to the Doppler shift, it would, for example, follow this red line. So you would have a dephasing of the two waves, the non-moving one and the moving one. And this is something you will be able to detect. However, when we read these papers and we got interested by the motion, we were wondering that only the Doppler shift was there, because the Doppler shift is something that only affects the time component of the gravitational wave. But the gravitational wave rays, or the wave vector, have 4 components. So there are also these 3 spatial components. We were wondering, is there something, what is happening with them? Is there something that we could detect? And indeed, we found that there is something that could be detected. For that, let me first explain you how the line of sight is related to the phase of the gravitational wave. The point is that the orbit of the source is, of course, related, or the orbital period is, of course, related to the period of the gravitational wave. For the T2 mode, this is basically the gravitational wave period is 2 times the orbital period. And you need a reference point to measure that, which is the line of sight. So you see your black holes revolving, and every time that passes by your line of sight, you count a new period. Now, what happens if the source is moving? For us, as a distant observer, it is so far away that the source looks to be at the same point. So in the observer's frame, the line of sight is always fixed, independent of the motion. However, the ray which is related to the ray which is reaching us in the source frame is going to be tilted due to the aberration. When the velocity is moving, like here, from left to the right, then the ray is going to be tilted to the left in order to reach the distant observer. And now what happens is, while the source is being accelerated and the ray is tilted, the reference point is changing. So when your black holes are revolving around and they get back to the point which would have been your reference point without the motion, it has already changed. And this will traduce in a phase shift, which is something we call the aberrational phase shift. Now we know that there are these 2 effects, and the question is, are they going to be detectable? Because we know that the Doppler phase shift is going to be detectable, the first thing we did was to compare the aberrational phase shift to the Doppler phase shift. On the left-hand side, I present the case for a kick source. And in the upper plot, we have a velocity almost aligned with the line of sight, and in the lower plot, almost perpendicular to the line of sight. The lines represent the phase shift induced by, in blue, the aberrational phase shift, green, the Doppler phase shift, and in red, both together. The first thing to see is that the aberrational phase shift, despite being a bit weaker than the Doppler phase shift, is of the same order than the Doppler phase shift. The second thing maybe to see is that the Doppler phase shift is becoming weaker the less the line of sight and the velocity are aligned, but the aberrational phase shift is becoming stronger. This tells us that the aberrational phase shift can tell us information about the components perpendicular to the line of sight, which is something the Doppler phase shift cannot do. But the most interesting thing is probably that both together, the aberration and the Doppler phase shift, which is what you really will see because you cannot decide to see just one of them, is always to be quite strong, because both together are always quite significant. So now let's get to the right-hand side, where I present triples. And in the upper plot, I present basically a triple where the period of the gravitational wave is 30 times shorter than the period of the binary on the third body, and in the lower plot, 300 times. And here in the middle, something in between. What we see here is that for the aberrational phase shift to be significant, these two periods cannot differ too much. Here, the aberrational phase shift is too small. However, when the timescales are somehow similar, the aberrational phase shift is going to be very significant and can again enhance your total phase shift a lot to almost double as strong as by only considering a Doppler phase shift. And how does this reduce in SNR? Here we have again plots of the same case as I presented in the previous slide, where I show how much SNR would be required to detect the particular phase shift over the velocity. So here, the lower the lines, the better, because it means you need less SNR to detect the effect. And for all of them, you see, okay, the aberrational phase shift is usually going to be more difficult to detect, but the important part is that the total phase shift, the aberration plus the Doppler phase shift, which I say again, is what really will be in your wave, is always going to be much easier to detect. In the best case from these 6, it's going to be 1.8 times easier to detect, which will reduce that you would be able to see 6 times more sources of this kind. Moreover, another important point is if you would say, okay, I don't care, I ignore the aberrational phase shift when you don't know it, and then you detect a particular source. For example, here you detect your phase shift, and this is somehow related or reduces into an SNR of 100. By only considering the Doppler phase shift, you would estimate that you have a velocity of 200 kilometers, 2000 kilometers per second, while the reality is that you have 1000 kilometers per second. So if you don't take the aberrational phase shift into account, you could be overestimating the information you're getting from your source. Now, to cut the long story short, what happens is, first of all, the center, almost all sources are going to have a center of mass motion of some kind. But despite this fact, they're usually not included in most of the templates. We know that if the velocity is time dependent, this is going to introduce a phase shift. The aberration and the Doppler phase shift, which can provide us information about the intrinsic properties of the source through, for example, the kicks, and extrinsic properties, for example, through the orbital motion. And what we have done is we discovered a new kind of phase shift, the aberrational phase shift, which can contribute to the detection of the motion and enhance its detectability significantly by, for example, allowing you to detect up to 6 times more moving sources. Okay. Thank you very much for your attention. Here is the reference I used in this presentation. And if you like the presentation, I in particular would like to recommend you the last one, which is the paper on which this work has been based. Thank you very much again. Bye-bye.